Christoph Thaele. So he'll be speaking on spherical splitting tessellations.
Thank you. Thanks a lot for the invitation, and I'm happy to be a speaker in your seminar today. And I would like to discuss with you a very important problem for mathematicians, namely how mathematicians, or more especially how should probabilists cut an apple. So imagine that you are hungry and you have an apple and you would like to cut this and you don't know how to do it and you are a probabilist. What could be a good choice? Well, you take your knife and maybe cut your apple first of all randomly into 2 pieces, and you cut through the midpoint of the apple, and then your apple falls into 2 pieces. And now you want to cut further because they are too big, but they are also too big to hold them in one of your hands and then to cut again. So you take one of the pieces and again you cut randomly with the knife one of these pieces into 2 pieces. Now you have 3 pieces, and now you are undecided and you choose one of the 3 pieces at random and you cut further. So the big piece has fallen into 2 pieces now, and then they are still too big for you to eat them, and you cut further into pieces and so on, right? And now you can also reassemble the pieces together to see how you did the cutting. And then the picture should look a bit like this. And what you see here is, well, ideally the apple is the surface of a sphere, so is a ball. And on the surface of this sphere, the cutting with the knife has left some traces, and these are these white stripes here. And so these white stripes, they cut the surface of this apple, so the surface of the ball, so the sphere, into spherical polygons at random. And this is what we call a spherical tessellation. And this is the topic for today. And to make this mathematically rigorous, we are not looking at the 2-dimensional sphere, but we are looking at the d-dimensional sphere, which is sitting in d+1 dimensional Euclidean space. And we do the cutting by random linear subspaces, and the trace, so the intersection of a random linear subspace or a linear subspace with the sphere is called a great hypersphere, and the set or the space of all great hyperspheres is denoted by this S sub d minus 1. And if you have a set on the sphere, let's call it C, and you would like to denote the set of all great hyperspheres that intersect or have non-empty intersection with this set, we write this in square brackets C. So this is the the set of all great hyperspheres that have non-empty intersection with this set. Obviously, this space of great hypersphere carries a unique rotation invariant Haar measure. We will work with this rotation invariant Haar measure here, but actually you can relax this assumption and work with more general measures on the space of great hyperspheres, but we will not go into this direction. And we want to do the cutting in continuous time, and at a certain point we would like to stop the whole process, and this time is it is a deterministic time at which we would like to stop all these is denoted by t. And now I will give you 2 equivalent descriptions of this cutting process of the sphere. The first one is an algorithmic description. So at time 0, we have also a tessellation of the sphere which only consists of one cell, namely the sphere itself. And tessellations will always be denoted by y. Y sub t is the tessellation that we have at time 0. So at time 0, we only have a tessellation which consists of one cell. We have a counter which we put to 1, and we have a random time which is at time 0, so at step 0 deterministic, it's just 1. So this is the initialization of this algorithm. And now whenever this counter is bigger than 1 or equal to 1, we suppose that a random time tau n minus 1 and the spherical tessellation y tau n minus 1 are already to us. And for each cell of this given tessellation, so for each cell, we generate an exponential random variable. We denote this by I sub c, which is, well, as I said, exponentially distributed. And the parameter is the measure of all great hyperspheres that intersect this cell C. And now we generate a new random time tau n, so that the waiting time between tau n, this new time tau n, and this given time tau n minus 1 is the minimum over all these exponential random times. And of course, again, this is an exponential, this is exponentially distributed. And now we have two possibilities. So either it's interesting, then this is the case where this tau n minus 1 is below our fixed time t. Then we pick a cell C with this probability here, so proportional to the measure of all great hyperspheres intersecting this cell. And then we pick, after we pick the cell, we pick a great hypersphere according to this distribution here. So this is a great hypersphere that's uniformly distributed among the great hyperspheres that have non-empty intersection with C. And then we make an update of our tessellation. We take this cell Cn, oh, sorry, here is an n missing, so this, we pick a cell Cn. We divide this cell that we selected with, according to this great hypersphere, and this is our new tessellation. So we split the cell Cn by this great hypersphere, so one of the cells is split, all the others remain unchanged, and this is how we update our tessellation. And then we run the whole process again until this time tau n that we generate is bigger than t, and then we output this tessellation. So how does it look like in pictures now in mathematical terms? So here's the sphere, and we already have we already did one splitting. So we split the sphere by one great hypersphere, and we rotated, so I rotated the whole thing in such a way that this great hypersphere is now the equator. And this equator has split the sphere into two parts, namely the upper half sphere and the lower half sphere. And then we make this random splitting. So randomly we have selected this upper half sphere. We have cut this upper half sphere by a great hypersphere. This has cut the upper half sphere into two spherical polygons. And now this polygon here has been selected, and this has been split now again by a great hypersphere. And now we have four random polygons, and we continue this thing recursively. Now we have selected the lower half sphere. I have cut this by a great hypersphere, and so on and so on. And if you run this for a certain time, the sphere is cut or is decomposed into random spherical polygons or high dimension polytopes. And this is what we call a splitting tessellation. And the algorithmic description is the way how to come up with such a splitting tessellation on the sphere. This is a nice description because it's easy to understand, but it's a bit more convenient if you want to do a rigorous probabilistic analysis to have a description of this construction by means of a Markov process running in continuous time on the space of tessellations of the sphere. So again, we are on the d-dimensional sphere, which is sitting in our d+1, and the space of great hyperspheres is again denoted by S sub d minus 1. We also need to do further spaces, namely when we cut the sphere with great hyperspheres, you have seen that the sphere gets decomposed into spherical polytopes, and the space of these spherical polytopes is called PD. This is the space of spherical polytopes of the spherical space SD. And the space of spherical tessellations, so tessellations of the d-dimensional sphere, is denoted by TD. So this is the space of all decompositions of the sphere into finitely many spherical polygons that are non-overlapping, so these polygons only intersect in their boundaries. And this is finitely many, as I already said. And now we formally define the splitting operator, and the splitting operator expects a tessellation cell of this tessellation and a great hypersphere that intersects this cell, and it outputs a new tessellation. And how is it acting? Well, if you have a tessellation and if you have a cell of this tessellation, and if you have a great hypersphere that intersects this cell, then you take out this cell from the tessellation. You decompose this cell into the two subcells that are generated by this great hyperspheres, namely the cell which is left or right in one of the two subspaces generated by this great hypersphere, and the other one, and you take these two new cells in. And if these conditions are not fulfilled, then you define this trivially, you just do nothing. And now you can also formally define a stochastic process, namely the splitting tessellation process YT. We define this with initial tessellation, the whole sphere. And by this, we mean the continuous time pure jump Markov process on the space of tessellations. And it's described by this following generator. This generator is called the calligraphic A. And on a tessellation and the bounded measurable function on the space of tessellations, it acts as follows. So you sum over all cells of this tessellation, you average over all the great hyperspheres that intersect this cell, then you update this tessellation according to this splitting operator, and you look on the effect that the splitting of the cell C in the tessellation C by a great hypersphere S has. And you do this, as I said, for tessellation T, spherical tessellation T, and a bounded measurable function on this space of tessellations. And this is somehow the continuous time Markov process description, which is completely equivalent to the algorithmic description that I gave at the beginning. And this gives you a stochastic process. And for any time t, the state yt is called the splitting tessellation. So it's a dissection of the sphere into non-overlapping finitely many spherical polytopes. So this is the object I would like to discuss with you today. And now, you know, when you have a Markov process, you have a lot of martingales that you can associate with this Markov process. And abstractly speaking, if you have a Markov process taking values in a Borel space, having a certain generator and a certain domain, then for any function of this domain, this random process here, so you take f of yt minus f of y at time 0, and then you subtract the integral from 0 to t, generating, should not be xs, but it should be, of course, ys here. And you subtract this term here. This is a martingale with respect to the filtration that is induced by this Markov process. And I would like to draw your attention to one technical detail that bothers us a lot, because our Markov process is taking values in the space of tessellations. And this space of tessellations has very bad topological properties. And for example, it is not known whether this space is a Polish space even. And most Markov process theory is developed for Polish spaces or even more special spaces. And it took us quite some time to find a reference which was general enough for us to deal with Borel spaces, because this is something that we can ensure. So our space is at least a Borel space. And this property here, this martingale property, this is usually attributed to Dynkin, so it's the Dynkin lemma. So in our case, this Markov process is the splitting tessellation process, and we would like to apply this lemma here, or this martingale property, to the splitting tessellation process. And well, the first thing that we will do is we introduce an interesting class of functionals. Namely, we fix a function that maps spherical polytopes to real numbers, and then we sum over all cells of this tessellation and apply this function to each of these cells of the tessellation. So this function could, for example, be the volume, the spherical volume of a cell. it could be the surface, the content of a cell, or it could just be one. Then this counts here, for example, the number of cells. And we will soon look at more interesting and more general classes of functionals that we can look at. And well, of course, you can apply, not directly, but with some workaround, you can apply this lemma here, this martingale property to this functional here, which gives us the martingale property of the following stochastic process. So the sigma phi of yt minus sigma phi of y0, and then you subtract this average that is written here. This is a martingale, and what we would like to do first is to apply this martingale property to an interesting class of functionals and to see whether something geometrically interesting comes out. And the first question is here, of course, what are geometrically interesting functionals which we can apply here? And we have already seen these functionals in the conical setup. Namely, Zaporozhets has introduced these conical intrinsic volumes. And if you identify a cone with the intersection of this cone with the unit sphere, these are the spherical intrinsic volumes that I would like to introduce in a slightly different but completely equivalent way. So if you have a spherically convex body, then you associate with it its spherical parallel set. So this is the set of all points on the sphere whose geodesic distance to this convex body is less than r. And then there is the spherical Steiner formula, which computes the volume of this R neighborhood, this spherical R parallel set of a convex body. And this can be written as a sum from J equal from 0 to D minus 1. Then there are some coefficients here. And then there is always this integral popping up. And these coefficients are the surface areas of lower dimensional subspheres. So these are basically constants that depend on J and the dimension of the sphere. Then there is a constant or a coefficient that depends on the convex set, the spherically convex body K. These are called the spherical intrinsic volumes. And then there is this term here. And if you are familiar with the Steiner formula in Euclidean space, you don't have such an integral here, but you will have just a monomial which appears here. But in the spherical setup, you will have an integral of combinations, or also products of trigonometric functions. And the spherical intrinsic volumes are exactly the conical intrinsic volumes, at least for spherical polytopes, that Zaporozhets has introduced. They have some nice properties. So for example, they are additive, they are rotation invariant, they are continuous with respect to a spherical Hausdorff metric, and they are all bounded by 1. And well, if you have a spherical polytope, then you can also rewrite these spherical intrinsic volumes in a different way, namely the J spherical intrinsic volume of a spherical polytope is up to a normalization, the sum over all J-dimensional spherical faces of these polytopes. Then you have the surface content, the J-dimensional Hausdorff measure of this face, and you multiply this by the external angle at this face. And here is a picture in 2 dimensions. It's not really spherical, but it's almost spherical. Here is our convex set, spherically convex set C. And well, if you want, for example, the 0-dimensional spherical intrinsic volume, then you have to sum over all 0-dimensional faces. Okay, these are just the vertices of this spherical polygon. The surface content of 0-dimensional Hausdorff measure is just 1. And what you do is you have to weight by the angle at each of these vertices. These are these external angles, right? And then at the 1-dimensional faces, the 1-dimensional faces are just these edges, here spherical edges. And well, one-dimensional Hausdorff measure is just the geodesic length, and you have to multiply with this external angle, and the external angle is just 1/2 here in this case. So it's the solid angle of a ray. And Zaporozhets, I think, explained that this is exactly 1/2 for faces of codimension 1. So these are the interesting objects that we would like to look at, and they also have local extensions, so measure extensions. So these measure extensions are obtained as follows. So you'll have a Borel set, so a set on the boundary of your spherical convex body, and now you don't look at the full parallel set, but you look only at the parallel set, a local parallel set. So if this is the set A, then this is just the local parallel set, and you do the same expansion in here, but you only look at points that are contained in this local parallel set, and then these local extensions, they behave like a measure. They behave like a measure in the second argument A. And these are called the spherical curvature measures. And these are our functionals that we would like to look at. So let's come back to our splitting tessellation construction. So you have your time. We have the index of our spherical curvature measures. We want to integrate a function against these spherical curvature measures that take a bounded function. And then we introduce these functionals sigma j at time t with respect to our function h. This is just defined as this sum. And this term here is just the shorthand notation for this integral. So you integrate over the spherical polytope C, the bounded measurable function against this jth curvature measure. And if you don't like this generality, then you can think of a special case. You just take j equal to d minus 1, and you choose your function, just the constant function 1, and then up to the normalization where you multiply with a constant. This is just the total surface content of all the cells in your spherical tessellation. And well, then we know from this Dymkin lemma that if you plug in functionals of this type, which are exactly the functionals that we are looking at, then this random process here is a martingale. And then we just need to recall how this generator looked like of this Markov process, this splitting tessellation process. And this generator had just this expression here. And what was this here? Well, you split the cell C in this tessellation by this great hypersphere S, and then you look what is the difference before and after splitting. So the difference is that there is one cell, namely this cell C, which gets split into two subcells, and you have to compare the effect that happens within this cell and all the other terms. So all the other cells are completely unaffected. So in this sum, they will just cancel out. So what remains here in this martingale is, well, at time zeros, you have nothing. It's 0. So you have this term here, the first term, it's this. This term is 0. And then you just have this time average. You sum over all the cells. This comes from here. You average over all the great hyperspheres that intersect this cell. And then you have this difference here. So this is after splitting, and you have to compare this with what happened before the splitting locally in cell C. Well, we said that these spherical intrinsic volumes are additive. So are their local extensions, the spherical curvature measures. So this sum here is just the spherical curvature measure of the intersection. So this is just the measure property of the spherical curvature measures. This is additivity or the valuation property. So all this greatly simplifies. And let us take expectation here on both, on both sides here. So on one side there is a 0, and we bring this one term just to the other side. So the expectation of this sigma j functional is just the expectation of this time average over all cells, and then average over all great hyperspheres of the jth in conical intrinsic volume or jth spherical curvature measures of this intersection. And this is now the point where spherical or conical integral geometry pops in and helps us to determine or to evaluate this experiment. Zakar has already shown us the conical Crofton formula, and in the spherical case, which is equivalent to the conical case, the spherical Crofton formula just looks like this. So if you average the J's spherical curvature measure, this just increases the index of the curvature measure by 1. This is the effect the spherical Crofton formula has, which means that the integral here, the inner integral that we see here, is just the same as phi j plus 1. So what you do now, you have the sum over all these phi j plus 1, but this is exactly the definition of our functional sigma j plus 1. So this is just sigma j plus 1. And now you play the same game again, right? You apply this Martingale property not to sigma j, but sigma j plus 1. You plug this in, take expectation, and you get another integral, of course, another time integral, and you play this game until you arrive at sigma d. Now you get the d minus j-fold integral over time, and then you arrive at this sigma d. But what is sigma d? Well, sigma d by definition is the sum over all cells. Then you have to integrate your function h over c. And you have some normalization, which comes from the normalization of this Hausdorff measure here, so not important. And so you now can make use of two things. The first thing is you have a spherical tessellation, so all these cells have disjoint interiors, and you can now apply the measure property of the Hausdorff measure to see that this is nothing else than the integral of h with respect to Hausdorff measure up to normalization. Well, and this holds for any tessellation at any time s. So this is just deterministic here. So there's no randomness involved. And now you can forget about this expectation here, and you can plug in what we computed. And then you can evaluate this default remaining time integral. And what you arrive is the following thing. So this expectation of our sigma j functional is just t is just proportional to the time our construction is running. So it's time to the power d minus j times some normalization times some factor that depends on our function h. And as I said, you can take j equal to d minus 1 and the function h to be 1, and then arrive up to normalization at the total surface area. What does it mean for our splitting tessellation process? So if you run in time, if time is running, you accumulate a total surface area proportional to time. Yeah. And what I would like to do next is to compare with another standard model from spherical stochastic geometry, which is the Poisson great hypersphere tessellation. So how is this constructed? Well, you take a Poisson point process on the sphere, which is rotation invariant and has intensity t. To each point, you associate its orthogonal complement. This is a hyperplane, a linear hyperplane in our d plus 1. And it cuts out a great hypersphere from the sphere, of course. So once you intersect it with the sphere, and you take the union of all these great hyperspheres that come in here. And the picture that arises is this guy here. And this is the Poisson great hypersphere tessellation of SD. And let's compute again, let's compute as well the total surface area that you see here. Well, this is just the expectation. The expected total surface area that you see here in this picture is, well, you sum over all your points and you take, well, the intersection of the orthogonal hyperplane intersected with the sphere. Well, but for each of these hyperplanes, the intersection is a full great hypersphere of dimension d minus 1, regardless what u is. And the d minus 1 dimensional Hausdorff measure of this guy is just beta d minus 1. And then it's just the expected number of points in this Poisson point process, which is t, because t was the intensity. And what you see here, if you compare, this is exactly the same as in our splitting tessellation. In our splitting tessellation, and our question that we would like to answer is, how can we distinguish this tessellation from each other? Because it seems that first order properties are the same, and actually if you are more careful, then you can also compute the expectations of all these sigma j functionals, and they will all be the same. So first order properties of these two tessellation models are the same, and we would like to see a simple characteristic that allows us to distinguish between the two models. And what is natural is not to look at first order properties, but maybe at second order properties. And that's what we would like, that's what we are also doing. So we look at variances, and we look at the variance of the sigma d minus 1 functional. So this is, you integrate your function h in the splitting tessellation yt against this d minus first spherical curvature measure. This is just up to a normalization, the same as the surface measure, the random surface measure induced by the splitting tessellation. And what we can do is to come up with an explicit representation of this variance. I will not show you the details of these computations, but I highlighted here a few keywords that are necessary to come up with this formula. You use again Martingale properties associated with the splitting tessellation process. Then you have to use a spherical integral geometry or conical integral geometry, and here it's not the spherical Crofton or conical Crofton formula, but there are integral geometric transformation formulas of so-called Blaschke-Petranchin type that you need here. There are also, with the same approach, you can also do covariances or variances of lower order curvature measures, but then results become more complicated. And as a special case, of course, you can obtain the variance of the total surface area by just plugging here h equal to 1 and then renormalizing. But just to give you a hint how this is done, so we use Martingale property of the following stochastic process. So you have the splitting tessellation process, and what you do is you do the time augmentation of, you look at the time augmentation of the splitting tessellation process. So you look at the process yt, t. So this is a Markov process then in the space of tessellations times time coordinate. And then you can apply, after some tricks, this Dynkin lemma again. You can compute the generator of this time augmented process, and you can come up with a new stochastic process, which is defined by this complicated or more complicated looking expression. This will again be a martingale, and then you apply this to products of functionals of the following type. So you have we have the sigma functional, which is suitably centered, and then we take the product with another sigma functional, which is maybe centered differently, and this already looks like, well, you can treat second order properties with this. But the approach here is a bit more complicated, but anyway, it's tractable once you use these martingale properties of this time augmented stochastic process together with spherical integral geometry. What I would like to highlight a little bit is the following thing. So you can read off from this formula the variance of the total surface area. So you let your process run, the splitting process run, and you stop at a deterministic time t, and then you look at the variance of the total surface content that has appeared until time t. So in 2 dimensions, that's just the total length of all the segments that you have drawn until time t. And this has, so here you have a double integral, but using something like spherical coordinates and spherical space, you can rewrite this as a single integral and even a single integral over the interval 0, 1 of simpler expressions here. So this is explicit expression of the total surface content of this spherical splitting tessellation. And what I would like to highlight is that there are not many models around in stochastic geometry where you can explicitly compute second order quantities. So usually you have you can do some asymptotic analysis, but explicit computations are rare. And we were very lucky that the splitting tessellation process is one of the models where you can come up with exact formulas that hold for any time t and not only asymptotically. But asymptotically, this picture is also interesting because there is a different behavior on the two-dimensional sphere than on any higher dimensional sphere. So you can do an asymptotic analysis with this expression here as the time goes to infinity. So let us go one-dimensional sphere and look at the sum of all length of all the line segments or geodesic segments that we have computed until time t, constructed until time t. Then this integral even simplifies, and who is a bit familiar with something like that, this is the logarithm of t times such an exponential integral, which has this definition here. These exponential integrals are obviously bounded, but as you can see here, there's the logarithm of t, and if you send t to infinity, of course, this grows like a constant multiple of the logarithm of t. So in particular, this goes to infinity as time goes to infinity. This means somehow that the fluctuations accumulate over time, and at any time the new segments, they have an effect on the fluctuations. This is in sharp contrast to what happens in dimensions bigger than 3 or equal to 3, because here you can have a look at this integral and see that this is bounded by this expression here, which is totally independent from t. So this expression here is just a constant depending on the dimension, but this is okay, but it's independent of t, which means that the variances stay uniformly bounded. And in intuitive terms, this means that somehow the fluctuations, second order fluctuations, they in this construction, they come from the very beginning of this construction phase. And then what happens after some time is not relevant at all. So this is only negligible or only contributes to a constant term. So this does not grow. And this is something which does also not very often happen in spherical stochastic geometry, that you have different behaviors for models in dimension 2 or in higher dimensions. And we could use this variance directly to compare this spherical splitting tessellation with the Poisson great hypersphere tessellation, but I will not do this directly. Rather than I will introduce another quantity which is a little bit maybe even more easy to handle, which can be introduced for any isotropic random measure m on the d-dimensional sphere. Let us denote by mu the intensity of this measure, so it's just the expectation of the total mass of this measure. And then we introduce what we call the spherical K function of this measure. This is an analog of a very well-known object in statistics, so which is called Ripley's K function for point processes or random measures in general in Euclidean space. And you can generalize this definition to spherical spaces. So what you do is you sample two random points, x and y, according to this measure mu, according to this measure m, and then you test whether their spherical distance is less than or bigger than r, and you average over all points, and you take expectation with respect to the randomness that's inherited in this measure mu. So it's somehow up to a normalization. It's the average distance of two random points that are located in the support of this random measure m. And if this function r, so of course this is a function in r here, and if this function is differentiable, then you call this the derivative the spherical pair correlation function. Yeah, so it's somehow the density of this guy. And what we can do is we can explicitly compute this spherical K function and the spherical pair correlation function of this random surface measure. So the measure is the following thing. So you construct your splitting tessellation, and then you put the d-1 dimensional Hausdorff measure on all the great hypersphere pieces of this tessellation, of the boundary of the cells of this tessellation, and this gives you an isotropic random measure on the sphere, and you can explicitly compute these two functions here, spherical K function and spherical pair correlation function. That's nice. But you can do the same also for the Poisson great hypersphere tessellation. You can compute explicitly the spherical K function and its derivative, the spherical pair correlation function. And this has also a nice interpretation. So the interpretation here is as follows. So those of you who know Sliven-Yak's theorem for Poisson point processes, these people should not be surprised that there are two terms coming from two different contributions. So you sample a random point here uniformly at random from this surface measure. So you put yourself on randomly on a great hypersphere, on such a great circle. There's your random point. You sample this random point here. And then there are two contributions. The second contribution, you see here, there's a power d minus 2 coming here. And this comes from the contribution that you see on this great hypersphere on which this red point is sitting. So this is just the total measure of the surface of the d minus 1 dimensional Hausdorff measure that you see in a spherical cup of radius r around this point here, which is sitting on this great hypersphere. This is exactly the second second term here. And the first term comes from, well, if you have a Poisson process, you can sample independently a new Poisson great hypersphere tessellation, and then you look at what happens around your point in a spherical cap of radius r here. And this is exactly what happens here. And this is why there is a factor d minus 1 here, because you have a d-dimensional spherical cap that you blow up around your point. And here you have the factor d minus 2, and this comes from the d minus 2 dimensional spherical cap that you blow up inside this great hypersphere on which this point is sitting. So that's why there is a sum of these two things. And you can, obviously, this is differentiable in R, and you can compute the spherical pair correlation function. This is just a derivative. And now we come to the conclusion. Well, we wanted to distinguish between our splitting tessellation and the Poisson great hypersphere tessellation, right? So their first order properties were the same. And what we would like to do is we would like to introduce a simple characteristic that allows us to distinguish between these two objects. And the thing is that we could, what we will use is the spherical K function, or more precisely its derivative, the spherical pair correlation function. We were able to compute this by Sliven-Yak's theorem for the Poisson great hypersphere tessellation. And we were able to do this using Martingale properties and the continuous time Markov construction for these splitting tessellations. And we can come up with two explicit expressions, and especially I plotted here the two spherical pair correlation functions. So the solid curve here corresponds to the splitting tessellation, and the dashed curve corresponds to the Poisson great hypersphere tessellation. And you can see these two guys are different. And if you want to compare them, for example, the K functions, this looks like 1 plus something, and you can also rewrite this as a 1 plus something, and maybe this is a bit instructive to do so. So you can rewrite this also as a 1 plus something. Even the coefficient up to this pi here is the same. And then here, this is 1 minus something. This corresponds somehow, that we do not construct full great hyperspheres, but somehow they got truncated here in this construction. So all these great hyperspheres got truncated. And this comes from a probabilistic, from the probability somehow that they got truncated. This is what is written here. This exponential term comes from the Markovian construction, whereas this exponential term doesn't exist here. This is just a 1 because we don't truncate. And then there is a t times sine of t, which comes here. And then this here is just a Jacobian when we transform into spherical coordinates. And what you can see here, well, these two simple characteristics are different, and they allow us to distinguish between these two tessellation models. And for both of these tessellation models, you can say much more. You can say something about other characteristics. You can compute different characteristics, also second order properties, first order properties. You can look at typical objects in such tessellations, try to compare them, try to make a link between them. And all this would be topic for a different talk, but yeah, here is the message. You can distinguish between but there are more objects and quantities that we could discuss. And for example, one could also discuss the links between these two models. There are very strong links between them. As you can already see from the formulas, they look quite similar. So there, you can ask for an explanation of why this similarity arises, and one could explain this. But since my time is over, I can't do this anymore. But if one of you is interested, you can look into our paper jointly with Daniel Hook that has appeared last year in EJP, and it's about the splitting tessellations in spherical spaces. And you will also find their references for this construction in Euclidean spaces, where this is now a well-established tessellation model, which goes under the name of so-called state tessellations, or tessellations that are stable under iteration. And yeah, we did similar things in spherical space, and we tried to highlight similarities and also differences between the model in spherical space and in Euclidean space. And if you're interested, I would be happy if you look into the paper or use the time that remains to ask questions. So thank you.
Okay, thanks a lot, Christoph. And so I think I will unmute the participants to give a round of applause now for Christoph. Yeah, I think everybody is unmuted. Okay,
yeah,
so
thank you.
Anybody wants to ask a question, they can ask. But I think maybe I'll first ask some questions which were posted in the chat. And so first, Shiva wanted to know that, I mean, something about the Martingale problem. Can you comment? Is it well, how do you see it as well posed? Zakar said it's not easy, but if you could comment maybe.
Yeah, so this was quite, how can I go back? I don't know. What do you see now? I don't know what you see.
We see the last slide. And
you see the last slide. Ah, that's interesting.
Now it's okay. Now it's okay.
Now it's okay. Yeah,
we see the Martingale one.
Yeah, now you see probably this thing. Yeah, so this is not easy, and you have to work quite a lot, and this took us a lot of time. We spent a lot of time to show well-posedness of this Martingale problem, and I think this is at least 15 or 20 pages in this paper. So if you are interested, please consult the paper. And especially you need some localization properties, because these functions here, they can be unbounded, and then you have yeah, you first have to localize, and then you get only a local Martingale, and then you have to convince yourself this local Martingale is actually a true Martingale, and all this takes a lot of technical efforts.
Okay, okay. There was one
which is not particular to the spherical setup, but this is also in the Euclidean case.
Ah, okay. It's even in the Euclidean, the domain is not. I mean, the space is not. You don't have nice topology, right? You'll still have a.
No. First of all, the space is ugly, so it's a Borel space, but we don't know whether it's Polish space. Also, the domain, so since the intensity function of this Markov process is number of cells, so this is unbounded, so you don't know, so we don't know what precisely the domain of this Markov process is, but yeah, for all the functions to which you want to apply this Martingale property, you have to you have to do a lot of work to convince yourself that it's actually well posed.
Okay. I hope. Yeah.
The main is not easy.
Okay. There was another question by Krishanu Kanta. I've asked him to unmute and ask since it's not clear to me. Krishanu, can you unmute and ask a question? I'm not able to see him. Why? Okay. So maybe let me ask a question in the meanwhile. You consider sum of phi, sigma phi. I mean, but also there would be some interest in considering maximum of the characteristics also. Is there something
Yes.
known?
In the Euclidean case, there are some known results. Nicolas Chenavier did work with that, but I think that there is an easier way to come up with some results like this, because it's usually easier to study this stuff for the Poisson great hypersphere tessellation first, because you have a Poisson process in the background, and well, it's much easier. But there is a translation. So there is a link between the splitting tessellations and the great hypersphere tessellations, which allow you to transfer some properties forth and back. And my impression is that you can also transfer some of these maximum things forth and back. But there is a paper in the Euclidean case, not in the spherical case, of Nicolas Chenavier and the co-author, and who study things like that. Yeah.
Okay, thanks. Okay, so anybody else wants to ask a question? Please feel free to unmute yourself and ask.
Yeah, I had a question.
Yeah.
In the formula KDT towards the end, when you showed the difference in the two models, so yeah, if I understand, why is there a reason why the t square and the t come in the second term in both the cases? Is there a simple explanation, or is it just a calculation? That
can you say it again? Why which?
In both cases, the second order term differ by t squared or t. 1 over t or 1 over t squared, right?
Well, one of these t's here corresponds to this guy here. So this is t divided by pi, and you have the reciprocal pi divided by t.
Okay, that's why. Okay, that's okay. Okay, so in some sense, right. So then, in some sense, the two models are kind of close by, right? If that's the explanation, that the t cancels off, and the second order almost the same for large t in some sense.
Yeah. For large t,
it will be the same. Okay, so they have. Is it known what happens as t goes? Okay, I know t goes infinity. The formula goes to something, but is there any other way to see the models the same as t goes infinity? Or do they have the same sort of stationary law in some sense, or?
Good question. I'm not sure.
Interesting. Now it makes sense now. There's 1 minus e to the minus t over pi. That makes sense. That cancels off 1t. That's good. That's good. Okay. So in some sense, they're very close by. Yeah, very nice.
Right.
Yeah.
Okay. So on the models, people look at where instead of just splitting, you have some splitting and merging. In some way, it's a reversible dynamics, or I mean, you would have a tessellation with some reversible dynamics, which can both split and merge or sort of coalesce.
I know that there were always discussion about this, but I have never seen something seriously written. Because it's the question, what do you take out? Yeah, I mean, taking in is clear, but taking out. So if you take out the segment, would you take out something like this here or not, or only segments that are not further divided? Or so it's not so clear how to take out. Yeah.
Okay.
So if you look at the picture, so there are some segments, for example, this one here, which has not split so far. You can take it out, and then the two cells will merge again. But
Yes.
you will never. So if you take out, for example, this segment here, which has already split in time, then you would maybe take out also these or not. And how do you do this? Would you like to extend them? And so it's not so clear how to make this taking out, how to do this taking out in a meaningful way.
Okay.
But I think it would be interesting to do something like this, to come up with a stable dynamics. Yeah.
Okay. Thanks. Anybody else has any other questions? Maybe I'll just wait a minute more and. Okay, so if no other questions, then we can unmute and once again give a round of applause to both Christoph and Zakar together. Okay, so let's hope that sometime maybe both Christoph and Zakar will come actually and give a seminar in Bangalore, maybe things improve and yeah.